Good morning, my dear SS1 students. My name is Dr. Mrs. Okeke Princess, Okeke PN. In this class today, we are going to look at two topics. And the first one is on work done in springs and elastic string. The second one is crystal structure. The objective of this lesson, by the end of the lesson, the students should be able to, number one, solve simple problems on work done in stretching or compressing a spring and elastic strings. Number two, define and explain elastic potential energy. Number three, describe the structure of simple crystal. Number four, give two examples of a crystal. Number five, distinguish between crystalline substances and amorphous substances. Now we go on with topic one. Work is done when an elastic material is stretched or compressed. The force stretching the material is F. The unit is in newtons. Then the work done is given by work done equals average force times extension. That will give us initial force plus final force divided by 2 times extension, whereby that initial force and final force over 2 is just representing the average force. Then mathematically, initial force, because it was at rest, so the initial force is 0 plus final force F all over 2 times extension. And when you can rewrite it again as half F times E, which is extension, and that is equal to half F E. But by Hooke's law, F equals KE. Because you remember we have treated Hooke's law in our last class. So by Hooke's law, F equals KE, hence work done, which we represent by letter capital W, equals half KE squared, where K equals force constant or stiffness. You remember all these ones where I'm calling came from Hooke's law. Note, the work done in compressing the material is also given by W equals half FE equals half KE squared. Now, with all these mathematical symbols, let us put it into practice in doing some calculations. Example 1, a spring is stretched 40 millimeter by a force of 15 newtons. What is the work done by the force? Now, let us look at the solution. Write out all the things given to you. F, that is force, is given to be 15 newtons. E, that is extension, is given to be 40 millimeter. Convert it to meters by dividing 40 by 1,000. Then you have 0.04 meters. Now the formula W equals half Fe. Substitute into this formula. Anywhere you see F, you write it 15, and anywhere you see E, it is 0.04. By the time you finish the substitution and simplify, you get the answer of 0.3, and the unit of work done is in joules. Is that clear? Question number 2. A spiral spring is compressed by 0.02 meters. Calculate the energy stored in the spring if the force constant is 400 Newton per meter. You can see in this one, write out all the things given to you as usual. Force constant, which is K, equals 400 Newton per meter. Extension 0.02 meters. Now bringing in the formula. Hence, W equals half KE squared. Do your substitution. Half times 400 times 0.02 to power 2. By the time you simplify this, your answer will be 0.08 joules. We are moving forward. The next thing we are going to look at is elastic potential energy. This is the energy possessed by a body by virtue of its state or position. It is stored energy which can be transformed into other forms of energy. For example, stretching the rubber of catapult and projecting a stone from it. The elastic potential energy stored in the rubber is transformed into the kinetic energy of the flying stone according to the law of conservation of energy. Elastic potential energy is also given by, still the same formula, work done, that is capital letter W, equals half Fe, which when we remove F, because of Hooke's law equation, we can substitute for F, and then we will now be having half KE squared. Is that clear? Example. A stone of mass 20 grams is released from a catapult whose rubber has been stretched through 4 cm. If the force constant of the rubber is 200 Newtons per meter, calculate the velocity with which the stone leaves the catapult. You can see you have to change so many units here. Instead of gram, you work with kg. Instead of cm, you work with meters. Now, solution. Let us look at the solution on how we can go about it. Remember that the elastic potential energy of the stretched rubber is transformed into the kinetic energy of the stone. That is to say, we will equate the formula for potential energy, elastic potential energy, to the kinetic energy of the stone. Hence, we will be having half ke squared equals half mv squared. We have equated the two formulas, the potential energy and the kinetic energy. Now, but we are looking for the velocity. We have to use something to represent that velocity. So by that, we now say, let the velocity of the stone be v meter per second. Mass of stone equals 20 grams, which was given. Convert it to kilogram, you will be having 20 over 1000 kg. Extension, small letter e, equals 4 cm according to the question. Converting it to meters, you will be having 4 over 100 meters. Force constant K equals 200 newtons per meter. We are not converting that one because it's already in the standard unit. Now, having listed all this, you now go back into that equation and do your substitution into the equation of half ke squared equals half mv squared. Substituting into it, we have half times 200 times 4 over 100, all in bracket, squared, equals half times 20 over 1000 times v squared. That will give you half times 200. When you open the 1 in the bracket, you have 16 over 10,000 equals half times 20 over 1000 times v squared. Now we proceed. By the time you simplify that, you will be having 4 over 25 equals v squared over 100. Through cross multiplication, in order to make v squared the subject of the formula, you cross multiply, you'll be having 25v squared equals 400. Making v squared the subject of the formula, you have 400 over 25, and all will give you 16. But remember, you are looking for v and not v squared. So you square root both sides. The square root of the one on v will cancel off the square there. That is the power 2 there. Then the square root will remain for that of 16. And square root of 16 will give you 4 meters per second. Is that clear? We move forward. So having done all these examples, I will give you some to do by yourself. Assignment number 1. A spring of force constant 1500 Newton per meter is acted upon by a constant force of 75 Newton. Calculate the potential energy stored in the spring. Number 2. When a force of 50 Newton is applied to the free end of an elastic cord, calculate the work done on the cord. Number 3. A spring stretches 10 cm when a force of 600 Newton is applied. What is the potential energy of the spring when it is stretched 12 cm? So with this, that's the end of that topic 1. We go over to topic 2. That is crystal structure. Under this very topic, we look at this. Solids are usually divided into two classes. There are the crystalline and non-crystalline or amorphous solid. That's if you don't want to call it non-crystalline, you call it amorphous. The distinguishing feature between the two is the arrangement of the atoms or molecules in the solid. So let it be clear to you that solids are divided into two classes, crystalline and the non-crystalline, which you can call amorphous solid. So we proceed. We pick them one by one. Crystals. What is this word crystal? Let us look at it. A crystal is a piece of solid matter in which the atoms, molecules, or ions are arranged in a highly regular repeating pattern or lattice. If you don't want to call it pattern, you can call it lattice. Crystals are the small particles of a crystalline solid, which grow out from the solution of the solid when the solution is cooled to freezing point. That's when you can get these crystals. Now, crystalline solids are usually soluble in water. Crystals can be identified and distinguished by their shapes. By their shapes, we can identify them. By their shapes, we can distinguish them from amorphous. Crystals with identical shapes are said to be isomorphous. When the crystals have identical shape, they are called isomorphous. Now let us look at the characteristics of crystalline substances. Number one, they have definite shape. That's if the shape is like a cube of sugar, you will see it. It is definite, it's not shapeless. Number two, they have definite melting and boiling point. Number three, they are soluble. That they can dissolve easily in water. Number four, they can exist either in hydrates or anhydrous form. Thus, hydrate has to do with water and hydrous has to do with no water. So they can exist in those two forms. Number five, they do not soften gradually when heated. So immediately you heat a crystalline substance, quickly it will just melt. So they don't soften gradually. Their own is in a rapid form. Number six, they solidify at a constant temperature. 7, they form crystals. Now, these are just their characteristics. Okay. Now we move forward. The structure of a crystalline solid can be, this crystalline solid can be arranged in 3 different ways. Number 1, simple cubic lattice. In this, the atoms or molecules or ions are placed at the corners of imaginary cubes, stacked side by side, up and down, like building blocks. as shown in the figure below. Examples. The structure of sodium chloride. Sodium chloride crystal is one of the examples of that. In it, that is in this sodium chloride crystal, the atoms of sodium and the chlorine take alternating positions in the cube in each of the 3 directions. Each atom within the solid has 6 immediate neighbors, as you can see in that diagram. That diagram is self-explanatory. That's the diagram of a simple cubic crystal, sodium chloride as the example. Now, the second arrangement, face-centered cubic crystal. Here, the unit cell has identical particles at each of the corners plus another in the center of each face, as shown below. Examples of such crystals are copper, silver, aluminium, lead, etc. You can look at that diagram there, face-centered cubic crystal. Example is that zinc sulfide. It's very clear there. Then number 3 arrangement, body-centered cubic crystal. This unit cell has identical particles at each corner plus 1 in the center of the cell, as shown below. Example, as shown below, you can see the diagram there. Each atom has 8 immediate neighbors. You can see it, body-centered cubic crystal diagram there. Examples of such crystals are chromium, iron, and the platinum salt. These crystal patterns are not actually seen by the human eye, but are revealed by X-ray diffraction. So don't just think that as you are looking into the air, you will now be seeing all those things. But we said it is revealed by what? X-ray diffraction. Now, having treated that of crystalline, what of the non-crystalline? The structure. Remember that I said another name for non-crystalline is amorphous. So let us look at the structure of amorphous substances, starting with their characteristics. Number 1, they have no definite shape. Number 2, they have no definite melting or boiling point. 3, they exist only in anhydrous form. Are you seeing it? Only in anhydrous form this one can exist. Number 4, they are usually insoluble in polar solvent. Number 5, they soften gradually when heated. Okay. Okay, they soften gradually when heated. Number 6, they do not form crystals. And number 7, they behave oddly when they are cooled. So with these very characteristics of this one and the crystalline, you can easily use it to become their differences, assuming you are asked to differentiate between crystalline substance and their amorphous substance. Their characteristics have already showed their differences. Is that clear? We move forward. Now let us look at the graphical representation of cooling and heating curve for crystalline and amorphous substances. The graphical representation. They are shown below. Look at their graph. The first one is showing the cooling curve for crystalline substance. You can see that graph there, the graph of temperature against time. The highest point, you see that line, the highest point, the temperature started dropping from the highest point, and at a particular point, it was steady. It was steady before it now changed again, started dropping. So that very point where it was steady is the melting point. You can see it in that graph. Now look at the heating curve for crystalline substance. For that heating curve, it started from the lower temperature. It started going up. When it was at the lower temperature, it was solid. So as you started heating it, it starts to melt into liquid. At a point there, you can observe melting point there. Then it entered liquid stage. From liquid stage, the temperature keeps on increasing. It entered gaseous state. Now the third graph there is about is amorphous. Temperature against time still. You say after heat is removed, that's when you get this shape of graph. Is no more under heating stage. Immediately you remove the heating, then it will cool, and then you see this shape of a graph. Now assignment. Question 1. Distinguish between crystalline and amorphous substances. Give 2 examples of each. Number 2. Distinguish between simple cubic crystal and the body-centered crystal. Please send the assignment solution to the school email. Is that clear? Thank you for listening. Stay safe and God bless you.